Hello, my name is Schilling, and this is joint work on reachability analysis of linear hybrid systems via block decomposition. The talk is structured as follows. I will first shortly explain what linear hybrid systems are and how you can do reachability analysis for them in a classic way. And then I will come to the main part, which is our new decomposed analysis algorithm. And then I will talk a bit more about the intersection operation, which is at the heart of this algorithm. And in the end, I will show some evaluation. Okay, so a linear hybrid system looks like this. So you have some locations, let's say on and off, and in that you have a differential equation, more precisely a affine differential equation. In this case, there's only one variable. In general, you have several of them. Then you have a condition called invariant, and this condition has to be satisfied for you to stay in this location. And then there are transitions. They also have a condition, and they are called guards, and they say that when you can take this transition. These linear hybrid systems are also called hybrid automata with affine dynamics, and the semantics are given by executions. So let's say we start in this off location, then at state 22, x equal to 22, then you can stay in that location for a while, x falls, and at some point between 18 and 19, you can take this transition, then you switch to the on mode, then x grows again, then you can take this transition, and so on. And this is non-deterministic, so you can start from any state that satisfies the invariant, and then the execution might look different. In general, this is the form of a linear hybrid system. So you have locations with affine differential equations, invariants and guards that are given by polyhedra, so intersections of linear constraints. And at the transitions, you can also have assignments. In this case, these are affine maps. So how does reachability analysis look like? Typically, so you start from a set of initial states. They are given. This is part of the specification here in blue. Then many approaches discretize time and compute an enclosure of all executions that are possible from this set of initial states up to some time step delta. And then you have a discrete system, and you can do some standard abstract interpretation to compute this sequence of, in this case, orange sets. And we call the union of these orange sets a flow pipe. And the idea is that this flow pipe covers all possible executions of the system. So this was the part for being in a location, but then when you take a transition, you have to check that you satisfy the guard. So you intersect with this guard, and then the set that you obtain, this intersection, you will then apply the assignment to, and then in this case, you get to this green set. And in the end, you check whether you found a fixed point, because when you found a fixed point, you can stop. And otherwise, you would have to continue from that location with the same algorithm. All right, so this was a very short introduction to linear hybrid systems and reachability analysis. And now we want to see whether we can do this more efficiently. And the key concept here will be that of Cartesian decomposition. Let's look at this three-dimensional sphere here, and let's project it to x1 and to the x2, x3 plane. In x1, we get an interval. In the plane, we get a disk. And now we can recombine these two sets with a Cartesian product to obtain a three-dimensional set again. In this case, this is a cylinder. And it's easy to see that this set will be a superset or an over-approximation of our original sphere. Okay, so recall this flow pipe that we computed in high dimensions. By the way, by high, in this presentation, I will always use 2 dimensions because I can draw them, but of course, everything generalizes to higher dimensions. So we have this high dimensional flow pipe, and there is an algorithm that we presented 2 years ago that computes a flow pipe in a projected space. So instead of computing this 2-dimensional flow pipe, we can efficiently compute the projection to 1 dimension, or in general to a lower number of dimensions. So let's say to the x1 dimension, then we get these projections or intervals. Okay, and now we want to use this algorithm in our analysis of hybrid systems. So the 2 key properties of this algorithm are that sets are computed in low dimensions, and the sets are decomposed, so they are Cartesian products of lower dimensional sets. So how can we use these properties? And we have to answer the following questions. So first, which dimensions do we need to compute? So we have an algorithm to compute the flow pipe in certain dimensions, but we still don't know in which dimensions we want to do that. And we want to benefit from these 2 properties. And the last point is rather an obstacle. So this algorithm that I mentioned requires a high dimensional input. So it's clear that we cannot just do everything in low dimensions. So here's the key idea. Recall this picture of the high dimensional flow pipe with the high dimensional guard intersection. And the idea is that we can actually compute this intersection in the projected space. So we can project the guard as well. So let's look at the guard. It's a linear constraint or half space, and the coefficient in the dimension x2 is 0. So that means this constraint is actually not constrained in this dimension. And we will exploit this because then you can write this set as a Cartesian product of a 1-dimensional half space and a 1-dimensional universe. So this guard is actually decomposed as well. And so we can just project it easily, and we don't lose any information. And then we can take the intersection with the interval. We know how to compute this interval using the existing algorithm. And then we can check for an intersection in 1D. So here's the algorithm in 3 items. So first you compute the flow pipe in low dimensions using the existing algorithm. Then you detect whether there's an intersection with the projected guard as well in low dimensions. And finally, if you found an intersection, then you have to compute the high dimensional intersection. Because as I said, we need a high dimensional input for the next location after the transition. So that means of our flow pipe, we compute the first set in high dimensions because that's what we need as the input. Then we compute intervals everywhere, but then we detect that there is an intersection with the last 2 sets, and so we compute them in high dimension as well. So in practice, of course, you would hope that you save a lot more than just 2 sets, but this is just for illustration. Okay, so we actually answered all the questions we had. So which dimensions do we need to compute? Well, we need to compute the flow pipe in those dimensions where the guards are constrained, because that's exactly the information that we need. We benefit from the fact that the flow pipe is low dimensional because we detect this intersection in low dimensions. And we also benefit from the fact that the sets are decomposed because well, we will see this in the next section, but this is also true for all the other operations that we will do, but I don't have time to talk about this. And the last obstacle is fine because we compute a high dimensional output of our flow pipe of the intersection with the guard. So we are not required to compute everything in high dimensions. All right, so this was the algorithm in a nutshell, and now let's look at this intersection operation because that is actually interesting. So this looks a bit technical, but it's actually very easy. let's say we have our decomposed set x hat, which is a Cartesian product of x1 and x2, and a decomposed guard g hat, which is a Cartesian product of g1 and g2, and x1 and x1 and g1 and x2 and g2 have the same dimensions. Then it's easy to see that if you write out the intersection, and you know that Cartesian product and intersection distribute, that you can take the intersection in this first component and take the Cartesian product with the intersection of the second component. This is illustrated below. So if x is a Cartesian product of these red intervals and g is a Cartesian product of these blue intervals, then their intersection is again a Cartesian product of intervals, namely those purple intervals, which can be computed as the intersection of these projected intervals and these projected intervals. And this generalizes to higher dimensions and also to unbounded sets. Yeah. As a corollary, we can say that the intersection of these two sets is empty if and only if it's empty in one of the components. So it might be empty in the first component or in the second component. And now we can exploit this further if we know that G2 is universal and assume that X2 is non-empty. So then the intersection of X2 and G2 is equal to X2 because G2 is universal. And since X2 is non-empty, we know that this disjunct is trivially true. So we can just ignore it and simplify this check to this first disjunct. And that's why I said we only need to look at guards in the constrained dimensions, because in the unconstrained dimensions, they are just universal. And we know by construction that X2, which would be the projection of a flow pipe, and a flow pipe is never empty. So we know that this assumption is also satisfied always. Okay, so here's a recapitulation. We have this high dimensional flow pipe and the high dimensional guard. And since it is unconstrained in the X2 dimension, we don't need to compute the intersection in X2 at all, because we know it will never be empty. So to check whether the intersection with one of these sets and the guard is empty, we just need to look at the X1 dimension. All right, so this was the simple part where X, hat, and G were decomposed in the same structure. But what if this is not the case? So what if G is not decomposed in the same structure or not decomposed at all? Well, then we can still decompose it using an over-approximation. So we can define G hat as the Cartesian product of suitable projections of G. And this will be an over-approximation. And then we can take the intersection with X hat and this new G hat as before. And this will, again, be an over-approximation of the true intersection. So using this idea, we can now come up with two algorithms. The first, or let's say that this is the setting. So we have this decomposed set X, which is a Cartesian product of lower dimension sets. Let's, for illustration, just say this is just one dimension each. And we have this high dimensional guard, which, let's say, is constrained in dimension 1 and 3. So the interesting sets will be X1 and X3. So first, the high dimensional algorithm would just say, we take this Cartesian product and we take the intersection with guard, and this gives us a high dimension set. This is of course exact, but it's very expensive because it scales with the number of dimensions. So here's an alternative, the very low dimensional intersection. You just take this one dimensional part of X and you project G to the first dimension, and then you compute the intersection and you get a set X1 tilde. And you do the same for the third dimension. And then you can take a Cartesian product of the original X sets, because as I said, G is unconstrained in the other dimensions, so the intersection will be the identity. And yeah, this is a superset of the true intersection. And this is very efficient, of course, because you can do everything in low dimensions. But in general, this projection can be super coarse. You can even obtain the universe here. That's why we actually suggest to do something in the middle. So we call this the medium dimensional intersection. You take the set x1 and x3 together as one set, as a two-dimensional set in this case, and you intersect with the projection of G to dimensions 1 and 3. So this is a two-dimensional intersection, and this is exact. But then you have to project again because you want to get it into the right dimensions as before. So for instance, you want to get this x2 set in between. So you have to project this result. But in general, this projection in this later stage is more precise than doing it first. So this is still quite efficient, but much more precise. All right, so this is about theory. Now we will talk about practice. So I have 3 experiments. The first experiment shows the scaling of our intersection operation in the number of constraint dimensions, k. The second experiment shows results for the full reachability analysis. And the third experiment shows the scaling of the reachability analysis in this number k. Okay, so this is the setup of the experiment. We have a 1024 dimensional hypercube and a simple half space as a guard, which is given like this. So x1 plus x2 plus and so on until xk for some parameter k less than 2. And this half space for any k properly cuts the hypercube, so this is a non-trivial problem. And here we have 5 algorithms to compute the intersection. The first one is our low dimensional intersection. The second one is our medium dimensional intersection. Then we have a simple heuristics to estimate the support function of the intersection. This is in general very coarse. Then we have another algorithm that estimates the support function of the intersection using optimization. This is much more precise. And the last one uses the exact polyhedra representation. And we remove redundant constraints, otherwise this would be a constant time algorithm. All right, so this is the results. In blue, you see our decomposed algorithms, and clearly they are the only ones that scale with the number of constraint dimensions. The other algorithms don't care because they do everything in high dimensions. And you can see our low dimensional intersection is the most efficient one, as you would expect. And it's actually more efficient even than this very simple heuristics. But in practice, it can also be very coarse. So we would rather advise to use this medium dimensional intersection, which still is very efficient for low values of k. And at some point you have a crossover due to some overhead in our algorithm, but that comes rather late. Okay, so now this was the first experiment. Now for the second experiment, we look at the full reachability analysis and we verify some safety properties. We have 4 algorithms that we compare. The first one is our algorithm. The second one uses this decomposition algorithm in continuous time that we presented 2 years ago, but doesn't use our new extension for hybrid systems, but just uses a high-dimensional black box algorithm for that, and this optimization procedure for the intersection. And the other 2 algorithms are implemented in SpaceX, which use a support function representation. Okay, before I come to the results, I want to quickly talk about the most interesting model. This is called a filtered oscillator, and you have 4 locations with a loop in the graph structure. We added an auxiliary variable to restrict the iteration to 1 loop. And the interesting thing about this model is that it is scalable in the number of dimensions. So you have 2 dimensions plus m filters, and the invariants and guards are only constrained in the dimensions x, y, and our auxiliary variable. So we have only 3 constraint dimensions, no matter what value m we choose. This is the ideal case for our algorithm. So here are the flow pipes. So you start here, stay in the location until you take the first transition, take the second transition here, take the third transition here, take the fourth transition here, go here, and then you realize that you found a fixed point because this variable restricts the iteration. So let's go from outside to inside. The outermost set is the blue set, which is our one-dimensional, low-dimensional intersection. And you can see it is the coarsest one, as you would expect. And it's even too coarse to prove the safety property that y is below 0.5 here. But then if you use our medium-dimensional intersection, this is the orange flow pipe. This is already sufficient to prove the property. Then there is this light blue flow pipe that uses two-dimensional blocks. So for blue and orange, we used one-dimensional blocks. And two-dimensional blocks generally give you more precision. And we can even, instead of using these box directions, we can use octagon directions, for instance. And in red, you have the SpaceX result, which is computed in high dimensions, and hence it is, of course, more precise. So these are the models that we will see in the next slide. The first one is a random model from a benchmark repository. These two models with two instances each are taken from the Arch competition. The first one is not good for our algorithm because it has most or even all dimensions constrained in the guards. The second one is good for our algorithm because less than half of the dimensions are constrained. And then there's this filtered oscillator with different numbers of dimensions or filters, where in each case, as you can see, we have only 3 constrained dimensions. So these are the models again. Here we have the algorithms. This is our algorithm. And in bold, I mark those columns that are the fastest for each row. So as you can see, except for this model that is not great for our algorithm, we are always the fastest. And for this filtered oscillator in high dimensions, we outperform the other algorithms by several orders of magnitude. And we can even scale to dimensions that are out of reach for these other algorithms. Here, this is the only algorithm that can compete roughly, but it is too coarse to prove the property. So you can actually say it's useless. And this is the final experiment for the scaling of our algorithm in the number of constrained dimensions. And yeah, as before, the high dimensional algorithms are really not affected by that. But our algorithm scales very nicely. This is a log scale, by the way. And only at the very end, we come to a crossover with SpaceX. But typically, you would hope for some k in this area, and then it's clear that this is much more efficient. So let me conclude. We have presented a decomposed reachability algorithm for linear hybrid systems. For that, we have integrated the existing decomposed algorithm for continuous systems into the hybrid loop. And the main ideas were to compute the low-dimensional flow pipe as before, and then detect the guard intersection in low dimensions, and then only if you need to compute the high-dimensional flow pipe for specific time instances. And this resulting algorithm is highly scalable, and yet it is quite precise under the appropriate conditions that your guards and invariants are only constrained in a low number of dimensions. But this is a very common thing. All right. Thanks a lot for your attention.